first designs prototype. Okay, then with respect to these specifications, you check whether this prototype is working according to all your requirements or not. Once it is checked, then you go for IC fabrication. Okay, so this in this domain, that is for prototype purpose, we use Xilinx, and for IC purpose we use CMOS layout design tools. Okay, so both these tools you will be working upon. So 4 assignments in this Xilinx tool and 4 assignments in CMOS tool. Okay, of course assignments are different, although the okay, so first 4 assignments, that is Xilinx based assignment, you need the project navigator as the Xilinx tool, that is the name of synthesis tool. So Xilinx is the name of vendor. Okay, and they provide you synthesis tool. Okay, so they provide you synthesis or simulation tools. Okay, so according to this Xilinx old version, the name of the synthesis tool is project navigator. So this is the name you must know in exam. External ask you which tool you have used, you answer Xilinx. Yes, Xilinx is the name of vendor. What is the name of the tool? Still again you answer Xilinx, because you don't go in detail what is the actual name of this tool. That is project navigator. Then project navigator, once you enter in this tool, specifications are known to you that you are supposed to design 2 input AND gate. So go to file menu, new project. Every time you should create your new project. For that, your project should reside in Xilinx folder. Wherever this Xilinx folder is, in whichever drive, you are supposed to store your project in Xilinx. Either you create your own folder or some bin whatever, it's okay, but path should be Xilinx. Okay, so give the name to your project. Then after giving the name to your project, deciding the location, go to source type selection. So here available sources means these are the ways of design entry. Okay, so either you want to have schematic entry, if you want to have HDL entry or FSM entry. So specifications can be entered in these 3 forms: HDL, schematic or FSM. Okay, so these are called as the design entry. Design entry can be done in these 3 ways. We are interested in HDL because we want to write some code. For remaining 2, schematic and FSM, you enter directly schematic of that particular design and you extract VHDL code. Similarly, you write FSM, draw that state diagram, and then you extract VHDL code. So here in these 2 cases you get HDL code ready. But we are interested in writing HDL code, so we will be using design entry as HDL. Next, again, on which hardware you will be dumping your code. For that purpose, you need to select the appropriate chip at the starting itself. Okay, so product category is all. Family that we are having is Spartan 3. Now family, you can say this is the surname of that family, Spartan 3. Whereas these devices are the family members, individual names of the family members. So these many family members are available in this Spartan 3. Okay, so out of these members, 400 XC3S 400 is the chip or the device available in our lab. So we select for XC3S. Now here, what is the meaning of XC3S 400? XC stands for Xilinx Corporation, 3S is Spartan 3, 400 is the number followed by K. So 400K equivalent gate count. Now you know the meaning of this equivalent gate count of the design. In second year, some circuit and or invert circuit was given to you, and you are asked to realize this using universal gates, either NAND gates or NOR gates. So suppose a circuit is there, you have realized initially using AND or invert ICs. In that case, you may need two AND ICs, one inverter IC, one OR IC, something like that. And when you realize this using equivalent universal gates, you come to know that to implement this much circuit, you need two NAND gate ICs if the gate count is more than 4 NAND gates, like that. Okay. So similarly, whatever is the hardware present inside this IC, what are the primitive elements of this FPGA? You have flip-flops, you have muxes, you have lookup tables, you have RAM memories. These are the primitive elements or basic components or resources of FPGA. Okay, so suppose this particular chip has got 100 flip-flops, some 500 lookup tables, 4 RAM memories, something 150 muxes. Okay, now if all these resources are replaced by universal gates only, either NAND or NOR, then in that case, to realize the complete hardware of this FPGA, you will need 400K universal gates. No hardware is there right now, but on this IC, whatever the resources in the form of these components are there, and if they are converted into using universal gates, you will need these many gates. This is the meaning of 400. So this is not simple 400 number, it is 400K. 400K equivalent gates are there inside the IC. Actual gates are not present in FPGA. Actual gates are not present. Whatever is present in terms of these components. Okay. So this is the meaning of this device number. Then PQ208, or these are the packages. These are the packages, and out of the available package, we have this package in our lab. So PQ is the name of the package. There are different packages, PLCC, then ball grid array, pin grid array, like this. So this is PQ, and 208 are total number of pins to this FPGA. Okay, so this is the package. And speed grade. This IC comes in two speed grades, -4 and -5. Don't read it as -5, -4. It is -5, -4. Now they are giving it speed and in terms of some numbers. So these numbers are nothing but nanoseconds. So speed is given in terms of nanoseconds. 5 nanoseconds or 4 nanoseconds. Now how this speed is in nanoseconds? Actually, it is pin to pin delay. Pin to pin delay. You know delay, you come to know speed. Okay, so the speed is mentioned indirectly in terms of pin to pin delay. So of course 4 nanoseconds delay and 5 nanoseconds delay, which one is faster? 4 nanoseconds. So delay is less, so that particular chip will be faster as compared to 5 nanoseconds delay. So again, these are the specifications we should select as per the chip which is there on board. Once you select this, then synthesis tool is existing VHDL that we have selected. Simulator is ISA simulator. Actually, Xilinx for initial versions of Xilinx tool, were without simulation tools. They were only synthesis tools. So Xilinx have provided synthesis tool, and compatible simulator tool was available from Mentor Graphics. And whenever both these tools are installed on PC, they get linked at the back end, and you can use both synthesis tool and simulator tool at that time. But nowadays Xilinx have introduced their own simulator tool, and this is ISC simulator. So there is no need of separate purchasing of simulator. Okay, so other simulator tools are Model Sim and Mentor Graphics. There are various tools also. Next, finish. Once you finish this, here the chip number, complete chip number with specifications is displayed. Keep this as highlighted. Go to project menu. Then new source. New source wizard, there are various options. Whether you want to write VHDL module, whether you want to write package, whether you want to write test bench, whether you want Verilog coding. So based on the requirement, you can go for the option. Our first job is to write VHDL module. So we will write VHDL module, and we will give name to this VHDL module. Name of the VHDL module should be self-explanatory name. So since we are designing and 2, I will write 2 input and gate, I will give the name A and B 2. If you write and cannot be used as name of the project because it is a reserved word, keyword being used. So you cannot give that name to the project or VHDL module. So and 2 means I am designing 2 input and gate. Next, I will give inputs A, B and Y as the output. Accordingly, I will set the mode in and out. If I want to operate on vectors, I will select bus, and accordingly I can set the values, whether I want 8-bit, 4-bit, accordingly. Right now I want to work on scalar quantity, input as scalar. I won't be keeping any bus part active. Okay. Next. Finish. Now, this is the template prepared by the tool for your module as and tool. What this template consists of? It consists of library IEEE. Now this is the basically IEEE is the library you need to include for standardization purpose. Okay, so IEEE have their standard norms. Okay, actually what happened, when initially at starting various companies have designed their own VHDL codes and all, but if those codes are compiled at some top level entity or at some other level, there were much difficulties in identifying the various parts of the code or at the time of compilation and all these things. So they have standardized all the documents of VHDL or hardware description languages under this library named as IEEE. Now this library IEEE consists of various sources, or you can say various resources required for HDL coding. Okay, so this is the topmost you can say topmost entity or topmost block in VHDL. It contains everything related to your VHDL code. Okay, so the name of the library is IEEE that we are using. Then these 3 are the lines which indicate packages. Inside this library there are different packages available. Okay, now here according to the sequence, now you can visualize that here library IEEE library consists of various packages P1, P2, P3. Then these packages consist of various functions, procedures, components like this. So more information you are getting as you come down from this IEEE, okay, or as you go enter deep inside IEEE, okay. So these are the packages named as IEEE library. Inside IEEE library there is standard package. This name of this package is 1164. 1164 again is the name of this package. This particular package helps you in using multi-level logic. Multi-level logic means up till now you have studied hardly 2, 3, 4, maximum 4 logic levels. 0, 1. You also know of don't care. Okay, this is the third logic level, and fourth one you might be knowing, that is called as high impedance, capital Z. Okay, so these are the 4 logic levels for digital circuits or in the form of inputs. Okay, but in addition with these 4 logic levels, there are some more 4 logic levels present in standard library, and all these are defined in this 1164 package. Then arithmetic operations are present in this arith package named as arith, and unsigned for signed unsigned format. Okay, so all these packages are present inside this library. All means whatever is present inside, everything should be visible here. All means everything from this package should be applicable here. Okay, so these are the 3 important packages, default packages given by the tool, and so we have to keep it. Means maximum resources you can use from these packages. Entity and 2AB of mode in, and this is the STD logic. Now this STD logic is a scalar quantity. If it is a vector, then in notation is STD underscore logic underscore vector some dimension, 3 down to 0, 2 down to 0. So this is the entity. Now this entity is nothing but a black box. What are the inputs of this black box? What are the outputs? That is only known to you. What is there inside is not known. So entity gives you the information of inputs and outputs only. Whatever is functionality of this AND2 is visible in architecture part. Okay, so in architecture part we write the functionality as y is equal assigned as a and b semicolon. Yes. Now this is the first step that we have done. HDL entry. HDL entry is completed. After HDL entry, then we perform syntax check. Now in this syntax check, we check if any error is there, syntactical error is there. So of course there is no error, but this is the syntax check is performed to see if any error is there in the code. Then after syntax check, what remains? You are supposed to perform simulation. It is called as functional simulation. Functional simulation means whatever I have written as A and B is assigned to Y, whether that is giving the correct functionality or not. Okay, so that is called as functional simulation, and here you can see only, or you can verify only the truth table as per the input combination 0, 0 to 1, 1. Okay, and you check what is the output, you compare it with known results, and you say that yes, it is working correctly according to the requirement. Yes, after syntax check, you perform synthesis. Now this synthesis is nothing but synthesis tool converts your higher level of abstraction to lower level. Means synthesis tool converts this HDL entry into primitive elements or netlist. Okay, or synthesis tool converts the HDL code into hardware. Easy way is synthesis tool converts HDL entry or HDL code into hardware in the form of netlist or primitive elements. Okay, so this synthesis tool converts higher level of abstraction into lower level, more details. Yes, after synthesis you perform again simulation. It is called as post synthesis simulation. Okay, now in post synthesis simulation, what is the difference between this simulation and this simulation? Yeah, this simulation, functional simulation, was performed before generating the hardware, whereas post synthesis simulation is performed after generation of hardware. Means for your hardware some logic gates are formed or hardware is formed, and whenever input passes through that hardware to the output, gate delay is visible. Okay, so with the simulation you get gate delay or delays come into picture in this post synthesis simulation. After post synthesis simulation, next step is implementation. Implementation consists of mapping, placing and routing. Suppose your hardware generated, you have written code for MUX. Okay, hardware is generated in the form of AND gates, OR gates, inverters. Okay, these are the primitive elements. Now these primitive elements should be identified on FPGA, that is called as mapping, one to one mapping. हार्डवेयर में क्या तैयार हुआ, उसका करस्पॉन्डिंग कंपोनेंट हार्डवेयर में, सॉफ्टवेयर में जो हार्डवेयर तैयार हुआ है उसका करस्पॉन्डिंग कंपोनेंट इज आइडेंटिफाइड ऑन चिप. Okay, that is called as mapping. Then placing and routing means performing interconnects between the different gates. So all these, after completing all this, if you perform simulation, it is post place and route simulation. Okay, in this post place and route simulation you come to know the total delay from input to output. Gate delays are involved, interconnect delays are also involved because circuit is connected. Okay, so interconnect and gate delays. Okay, so this way, after implementation, if you perform simulation, you come to know whether my circuit is getting slower or it is faster, and accordingly you can take corrective measures before dumping it onto the hardware. So this is the advantage of performing all these stages before implementation. Then last step is verification. Verification means dumping the code onto the FPGA. For this, third tool comes into picture. It is called as impact. Impact tool. Okay. So synthesize. Synthesis means you will come to know what is the hardware generated for my AND gate. So now here RTL schematic. What is RTL schematic? You write here code. Okay, suppose I am not taking the example of AND gate because there is no additional hardware. But if you design MUX, in MUX is completely combinational circuit. There is no any sequential part. Okay, so suppose you design shift register. In shift register there is combinational logic as well as flip-flop, means sequential part. So in that case, this tool, synthesis tool, converts your hardware into register transfer logic form. Register transfer logic means any code is all converted into registers and in between combinational cloud. This cloud indicates combinational circuit. Okay, so this R is nothing but flip-flop sequential part, and this is combinational part. In case of mux, only this combinational part will be there, this R will be absent. It is mux is totally combinational, but in case of shift register, you need both. The tool converts your code in this form. It is called as RTL logic. So RTL schematic. मी दाखवते दुसऱ्या याच्यावर तुम्हाला एकावर होते. Okay, first you occupy one PC and start writing the code of 4:1 mux.